Good afternoon. My name is John Humphreys. I work for Texas Instruments in the compiler team. So TI is a hardware company, and they produce a wide range of programmable processors, and it's our job to develop compilers so that users can program them. And we have processors all the way from very small microcontrollers all the way to our high-performance VLIW DSPs. And so what I wanted to talk about today is where I am at evaluating how well LLVM works for or targets our DSPs. And what I'd really like to do is kind of share where I am and some of the issues I'm facing. If there are those of you who are also working on these things, I'd like to work together. And of course, if there's something I'm doing that you've tried and didn't work, please let me know. So the approach that we wanted to take, and the really nice thing about LLVM is it's very modular, okay? And so the approach we wanted to take is kind of a hybrid where we don't want to write a backend, LLVM backend for our DSP just yet, because that's quite a bit of work and there's a lot of performance sensitivity about it. And so what the approach that we took is to write a translator that will translate from LLVM IR into our compiler's IR. And so I've got a little slide here. This is my one and only slide, so I hope that I can keep your attention with just one slide. So if you look at on the left here, this is, well, they're both just a traditional compiler flow, and on the left is ours, where we have a front end that generates what we call I-code, and then we have a high-level optimization path that also produces I-code, and then we have our code gen, our assembler. It's very similar to the right side where we have LLVM. And so the approach that we're taking is we've written this translator that's sitting in the middle, and it provides us lots of options. We can use Clang to compile our code, and then we can immediately convert it over to our I-code, run it through our high-level optimization, or go right into the to the code gen. And then we also have the option of running the LLVM high-level optimizations before we then convert over, and then either run our optimizer as well or go straight to our code gen. Okay, so I did this, and so we have the translator, and the experiment number one was to convert right out of Clang into I-code and run through our optimizer. And the experiment was to run on this large collection of loop kernels that we have that we evaluate our compiler with. And what I found is that what I'm calling the hybrid flow through Clang got about 60% of the performance of our native flow. And so why is that? So I looked into that, and it was obvious once I looked into it, but we've got a lot of user annotation capabilities and mechanisms that Clang does not have. So we have a lot of pragmas that you can place around loops to describe what the trip count, the iteration counts are, the min and the max expected. We've got an unroll pragma that tells the compiler how much to unroll a loop. And then we also heavily rely upon restrict, and we use restrict locally, not just for function parameters, which Clang and LLVM really only use restrict for function parameters. So I kind of took all those features out of our tool just to try to get apples to apples, and it accounted for about 25% of the performance. So you can see that explains quite a bit of the drop. And so kind of call to action number one is if we take this path seriously, I really want to look into adding some abilities to LLVM where we can annotate some of the loops to describe how much you want to unroll it and things like trip count information, and then also look into restrict and see if we can start using that at the local level. Okay, and then so experiment number two is where I actually ran it through the LLVM optimization and then converted it over, okay? And just take a wild guess. It got much worse. So apparently the LLVM optimization and our optimization don't work so well together. And so in looking into that, there are a couple of things that really stood out. Number one is that our I-code is not SSA based, so I had to do fee node instantiation, and that caused a lot of temporaries, which really confused our optimizer. And so where I am right now on this is thinking about implementing this translator as an actual LLVM backend so that I can make use of the target independent optimizations in the back end, like the fee node, the strong fee node elimination, and maybe the copy coalescing to help out with that. Okay, and then for future directions, Eventually, we would like to do an LLVM backend for the target, and it's a VLIW. So there's some issues that we're going to be facing that I would love to have help with. For example, we have multiple data paths in our architecture, so we have this partitioning optimization that is very important, and then we live and die on software pipelining, and so that's a very important part. And then we have an unprotected pipeline with some pretty big latencies, so things like global instruction scheduling are very important to us. So thank you.